Let's take a deck of playing cards and see how many ways we can arrange them into perfect rectangles. We'll take away the joker, so we're working with a deck of 52 cards. Our goal is to find all the combinations of rows and columns that will make complete rectangles. We can start with the simple solution of arranging the cards into one long row. This gives us a rectangle that's 1 card tall and 52 cards wide. We could also rotate the cards and think of this as being 52 cards tall and 1 card wide. To find additional solutions, we can consider how a deck of cards is structured. We have an equal number of red and black cards, so we can arrange them into 2 different rows of red and black. This gives us a rectangle that's 2 cards tall and 26 cards wide. Or we could spin them to make a rectangle that's 26 cards tall and 2 cards wide. Beyond the colors, the deck is divided evenly between 4 different suits: hearts, spades, diamonds, and clubs. Each suit contains 13 cards, so we could make another rectangle by laying out each suit in its own row. This gives us 4 rows of 13. Again, we can spin the cards and think of this as 13 rows of 4. Beyond the 2 colors and 4 suits, there aren't any other obvious ways we could break down the deck, but there still might be some other rectangles we could make. We could try making a rectangle that's 5 cards tall. With this height, we'd end up with a gap that would take 3 more cards to fill, so this won't work. We could try a height of 6, but again, the rectangle is incomplete. We can try other arrangements with a height of 7 or 8, and so on, but we'll find that we can't make any other complete rectangles. From this experiment, we found the only complete rectangles we could make with a deck of 52 cards would be 1 by 52, 2 by 26, 4 by 13, and then 13 by 4, 26 by 2, and 52 by 1. These are all the numbers that will divide into 52 with no leftover parts, which we call factors. The factors of a number show us how we can cleanly break apart a value using division. When we want to simplify a pattern or break it apart so we can figure something out, factors are a key for disassembling things that are combined with multiplication. Let's go back to our cards and add the joker back in, giving us a total of 53 cards. We'll see what rectangles we can make now. We can make the obvious 1 row of 53, or 1 column of 53. Beyond this, let's see what else we can make. We can no longer stack the cards in rows of 4, because we end up with 3 rows of 13 and 1 of 14. With another card added in, our previous factors aren't going to work. In fact, trying all other combinations, it looks like we can't find any other factors for 53, other than 1. Any number that has no factors besides 1 and itself is called a prime number. Prime numbers are special in that they serve as a sort of dead end for division. With no factors, prime numbers can't be cleanly broken apart with division. To try and force another rectangle out of the 53 cards, we could just take matters into our own hands and tear the joker into 4 equal strips. This would allow us to make 4 rows of 13 and cap off the ends with bits of the joker. While this may be a creative solution, when we think of factors, we don't consider fractions. Only whole numbers can be factors. While 4 times 13 1/4 does equal 53, we don't consider those to be factors of 53. This might seem like we're just making up a rule and excluding fractions out of spite. But if we consider fractional values as possible factors, it essentially ruins the idea and usefulness of having clean, simple values that can divide numbers apart. Consider this: if we change the rules and allow ourselves to chop up the cards in order to make a rectangle, we could toss the deck into a blender and grind up the cards into tiny little flecks. Pouring out the card bits, we could then make an infinite number of rectangles with our wad of mulch. While it is possible to divide values by fractions, finding factors gives us nice clean markers to indicate how a value can be evenly broken apart.